Okay, so this is my brief synopsis of the first lecture about thermodynamics. Just remember that the goal of this presentation was to build an intuitive understanding of thermodynamic concepts. And in particular, we're trying to understand the four laws of thermodynamics in a useful, intuitive way with a few equations, but we're not going to do the kind of depth that you would do in a really focused thermodynamics class. I gave you a brief overview of the four laws. Obviously, we are going to, over the course of all the thermodynamic lectures, go through each one of these laws in some detail. In this particular lecture, I went over the zeroth law and the first law and just started the discussion of the second law. And so that's what we'll do here in the synopsis. We talked about the nature of heat and temperature, did a little bit of historical thing about, originally thought of heat as a substance that passes from objects to objects, hot objects, passed a fluid to colder ones. Eventually got around to the idea that that didn't really happen. And in fact, that heat was a manifestation of motion at the molecular level. So it's the kinetic energy of the individual atoms and molecules that that is heat energy. And Count Rumford showed that you can convert work into heat. So if I put work into a system, I can make the molecules start to move around a little faster and they'll have a little bit more kinetic energy. We talked about temperature, very sort of intuitive kind of way, in the idea that the zeroth law of thermodynamics gave a more physical meaning to the concept of temperature, not this intuitive, oh, I touch this and it's hot, and I touch this and it's cold, but more along the lines of understanding temperature through the idea of thermal equilibrium. Uh, Gave this sort of pictorial description of the zeroth law, this idea that if two objects are at the same temperature, if you put those two objects in contact, they would be at thermal equilibrium. Or if they were at different temperatures and you put them in contact, when they reach thermal equilibrium, they would be at the same temperature. So that's the zeroth law in a nutshell. Pretty intuitive. You already knew it, had assumed it in everything you'd ever done, pretty much. Um, Here's some more details about the zeroth law of thermodynamics. Don't need to beat that particular horse. Um, and just, we know already, have long been using, all of us, the different temperature scales. And just remember my suggestion that whatever temperature I give you for anything in any problem, or not just a homework problem, just over your career, anytime you're given anything in any temperature scale, convert it to Kelvin before you start to do calculations. And that will prevent accidents and errors. So we talked about the total energy of a body. So we're starting to set up the first law by talking about the total energy of a body. And we said that the total energy was the kinetic energy, and this is the kinetic energy not of the individual molecules, but of the whole body, plus the potential energy. So this is the energy you get when you put something up in the air, you compress it into a spring or things like that, plus the thermal energy, and that is the kinetic energy of the individual molecules, plus chemical energy. So this would be energy stored in chemical bonds and things like that, plus electrical energy. If you had some charge on the device, we may be storing electrical energy in it. And that would be the total energy in the system. And then we said that total energy can be changed by conversion of mass to energy or by adding work or heat. Heat refers to the transfer of energy between two bodies due to a temperature difference. Remember, later on, I told you that there was one little addition to that there was, like, for example, if we put in optical energy, we're going to consider that putting in heat energy, even though it didn't happen because of a difference of temperature between the two bodies. Okay, so you could measure heat in the same units as energy, but often it'll be given to you in something that's a little different, like calories or BTUs. That's historically just connected back to the idea that maybe heat was this fluid that flowed around, but you can easily convert calories and BTUs to joules, and that's what you ought to do usually in most problems. We talked about thermal properties of materials. Heat capacity measures a substance's ability to retain heat. So if you had something with a high heat capacity, if you made a very small change in its temperature, you would be storing a lot of heat energy in it. If it had low heat capacity, you're going to have a small amount of heat energy stored in it with a small change in the temperature. We talked about the specific heat, And that's just the heat capacity normalized to the mass of the substance. So the SI units for specific heat would be kilojoules per kilogram per K. We talked about the thermal conductivity, which is the measure of body's ability to conduct heat. We talked about things that were really good conductors, and you might use them to enhance heat transfer away from something you're trying to keep cool. And then we talked about things that were very poor conductors, which made them very good insulators. And those would be things you would do to try to keep heat transfer happening across a boundary. Okay, we said that heat and temperature are related, and through this relationship that involved the specific heat, and we say that Q, this is the amount of heat that is transferred from one place into a substance, is equal to the mass of that substance times the specific capacity, heat capacity, times the change in temperature. So we can use that to figure out how much a temperature, how big a temperature change we would get if we put a certain amount of heat energy into a substance, or we could understand by measuring the temperature change how much heat energy came in. This just shows you some specific heats for some different materials. And you can see, for example, water has a really high specific heat, but then metals usually have a much, much lower specific heat. And then things like, concrete, glass, all those things are usually lower than what you have with water. We talked about work, the other way to change the energy of the system, and you should understand that work has to do with a force that applies and moves an object. It's not just applying the force, but you have to have some displacement of the object for there to have been work done. We talked about if the force and stays constant, then we could just calculate the work done just by this simple equation that doesn't involve any integrals. Okay, here we do have to use this dot product. So it's just the part of the force that's parallel to the direction of travel that's going to do any work. And if the force changes as a function of time or a function of distance, however it changes, then we have to use the integral form of the equation to calculate work. Don't forget there's a link here that you can go to a YouTube video and watch something that talks about calculating work done by applying force and moving an object. Okay, we did a sort of a pictorial, visual description of the first law, and we said an isolated system. Remember, an isolated system, we're not letting any energy come across the barrier, and we're not letting any matter come across the barrier. So in an isolated system, the first law of thermodynamics says the energy remains constant. The energy in that system never changes. It may change form. It may change from kinetic energy to potential energy, or into bond energy, chemical bond energy from one of those other two energies. It may change form, but the total energy never changes. And then in a closed system where we're not letting any matter go in and out of the system, but we do let heat and work go across the boundary of the system, then the change in the energy of that system is the amount of heat that either went in or out, plus the work that either went in or out. And then we said in an open system, it gets a little bit more complicated, that the change in the system energy now, because we're going to allow mass transport, is not just the change in the heat that crosses the boundary and the work that crosses the boundary, but we also have to consider the mass transfer. So things that come in may have a different energy than the things that went out. And so there will be a change in energy depending on what happens with the mass transfer. That's the visual version of the first law. Then I gave you the words, which basically said what I said when I was describing the picture. But then the important thing out of this slide was the equation here. So this is really the first law written in equation form. So we've got this internal energy. So the delta E is going to be equal to whatever changes we make in the internal energy. And remember, I told you for the most part in this course, that's just going to mean the change in the temperature of whatever is in our system. Okay, plus the change in the potential energy, plus the change in the kinetic energy. And that's going to turn out to be equal to Q. This was the heat transfer across the boundary, plus the thing we're going to call shaft work. And this is work done on the system. It can also be work done by the system if the work on the system that the system does isn't expansion work. But then we put the expansion work out here as a separate term. So if the system does work or has work done on it by changing the volume and the pressure, then we have to calculate this term, which could be an integral from the initial volume to the final volume of P as a function of volume dV. So you may have to calculate that to get the delta E. Anyway, here's all those terms described, and that's the equation form of the first law. And this was just a little thing that pointed out that if P of V equals a constant, then you can simplify all that down just to P of delta V. And I also pointed out, I didn't have it written here, I probably should write it down, but I also pointed out that if the volume doesn't change, then there is no expansion work. And that just goes back to the fact that work requires something to move. I gave you this practical way of thinking about the first law, practical ways to think about the first law. The important one is you can't get something for nothing. If the energy in your system of interest went up, the energy of some other system somewhere went down by the same amount, which is basically the same way of saying conservation of energy, that the total energy is staying constant. It just changes forms and it moves around. I pointed out something that doesn't matter for this class, but conservation of energy is not truly universal. That's because the expansion of space. But for every system we study, and probably for every system you'll ever study, it is an absolute truth. We talked about enthalpy. Enthalpy has this definition. It's equal to the internal energy plus the pressure times the volume. So that's the energy. Basically, this is the energy to create the system. Specific enthalpy is the same thing. It's just normalized to mass. And even though it's technically supposed to be a small h, we usually just use a large H, and it's just not bold. Okay, you can go through all of those. All these terms are described here, are defined for you here. And later on, I just sort of mentioned to you that it's not going to be immediately obvious to you why enthalpy is going to be a useful thing for us. But when we get to steam tables, you're going to see that it's going to be a really useful thing for us to be able to understand how much heat energy went in or out of the system, depending on what enthalpy we look out for the conditions that the system was when we started, in the enthalpy where the system was when we ended. We talked a little bit about this idea of putting energy in, and for example, into an ideal gas, and that energy is going to go into both changing the temperature of the gas, and it's going to go into expanding the gas if it can expand, if it's in a chamber that can expand. And there I mentioned to you that when you look up specific heats for gases, you'll find two. One is the specific heat at a constant volume, so it's in a container that can't expand. And in that case, all the energy will go into changing the temperature of the gas. And then there's also a specific heat capacity for a constant pressure. And in that case, we're going to have expansion, and some of the energy is going to go into the work of expansion, and the rest of the energy will go into changing the temperature of the gas. Okay, then we talked about questions that the first law cannot answer. And the first law, there's nothing in the first law that explains to us why heat energy spontaneously moves from hot objects to cold objects and not the other way around. And the first law doesn't tell us what percentage of heat energy can be converted to mechanical work. The only thing the first law rules out is that it can't be greater than 100%. So we can't get something for nothing. So that's all it rules out. And also, the first law doesn't give us any insight into why there's a preferred direction of time, why we experience a perceived time moving in the direction that we perceive it moving. And so it's going to turn out, to answer those questions, we're going to have another law. And that, of course, obviously, that's going to be the second law of thermodynamics. So I started to kind of ease into that topic by pointing out to you that heat energy is a statistical phenomenon. And what I mean by that is it's distributed across all of these molecules that are in the system, but these molecules are moving in random directions, banging into the walls and bouncing around and changing their direction. And so it's a very statistical phenomenon where mechanical energy, mechanical work, so if like I'm moving a piston in a direction, well, that's very deterministic. It's moving in one direction. It's not moving in all directions all at once and then banging into something and changing directions. It's a more deterministic thing. And this mismatch means that not all heat energy can be converted into useful mechanical work. Now, remember the thing I told you not to get confused about. Don't confuse this fact that I can't convert all of that heat energy perfectly into mechanical energy. Don't confuse that with losses due to things like friction or heat leakage. This energy isn't lost. It's just not available to be converted to mechanical work. It's going to actually get transferred somewhere else. We A place we wish it didn't get transferred, but it is, and we're not going to be able to extract it for mechanical work. So don't forget, don't start thinking, oh, we lost some of that energy because of friction in the machine or heat in the machine. We're going to start out by assuming perfect machines with none of those losses, and we're still going to find out that we can't convert all the heat energy into mechanical work. Then I started this this YouTube video from Veritasium about entropy, and just did the very first part where he was asking a bunch of people about what do we get from the sun. And remember that I referred back to what I talked to you about in the first lecture, where I said, we get a certain amount of energy in from the sun, we radiate out almost exactly the same amount of energy. So if the net energy flow is zero, what is it we get from the sun? And several people in the class just immediately said what we get from the sun is low entropy. That is right. That's exactly what we get from the sun. And I started this video talking about it. I'm going to show the rest of the video, but there's the link to it right here in the slide. And if you want to go look at that on your own, then that's a great thing to do. So that's where I ended that particular, lecture. And I'm going to pick up from this video next Tuesday. I'll start there, and then we're going to move on, and we will dive into some detail with entropy and try to understand that and understand how that limits the energy systems that we're going to study for the rest of the semester. Okay, so that's that. That ends this synopsis for this particular lecture, and I will do one for the next lecture in a new video. Thank you.